This article outlines the basic procedures for measuring trees for scientific and champion tree purposes. It does not cover timber assessment for production purposes, which is focused on marketable wood volumes rather than overall tree size. Tree height is the vertical distance between the base of the tree and the tip of the highest branch on the tree, and is difficult to measure accurately. It is not the same as the length of the trunk. If a tree is leaning, the trunk length may be greater than the height of the tree. The base of the tree is where the projection of the pith of the tree intersects the existing supporting surface upon which the tree is growing, or where the acorns sprouted. If the tree is growing on the side of a cliff, the base of the tree is at the point where the pith would intersect the cliffside. Roots extending down from that point would not add to the height of the tree. On a slope, this base point is considered as halfway between the ground level at the upper and lower sides of the tree. Tree height can be measured in a number of ways with varying degrees of accuracy. Tree height is one of the parameters commonly measured as part of various champion tree programs and documentation efforts. Other commonly used parameters outlined in tree measurement include height, girth, crown spread, and volume. Additional details on the methodology of tree girth measurement, tree crown measurement, and tree volume measurement are presented in the links herein. American Forests, for example, uses a formula to calculate big tree points as part of the Big Tree program that awards a tree 1 point for each foot of height, 1 point for each inch of girth, and 1/4 point for each foot of crown spread. The tree whose point total is the highest for that species is crowned as the champion in the registry. The other parameter commonly measured, in addition to the species and location information, is wood volume. A general outline of tree measurements is provided in the article Tree Measurement, with more detailed instructions in taking these basic measurements is provided in the Tree Measuring Guidelines of the Eastern Native Tree Society by Wublosen. Maximum heights. The tallest tree in the world is a coast redwood growing in Northern California that has been named Hyperion. In September 2012, it was measured at 379.65 feet tall. There are 7 other coastal redwoods known to be over 370 feet in height, and 222 specimens over 350 feet. There are only 5 species known to grow over 300 feet in height worldwide. There are historical accounts of extremely tall and large trees. In the northeastern United States, for example, there are frequent stories published in newspapers and magazines dating from the 1800s telling of extremely tall white pines. One extraordinary account in the Weekly Transcript, North Adams, Mass. Thursday, July 12, 1849 reads, "A large tree, Mr. D.E. Hawkes, of Charlemont, cut a pine tree a short time since, of the following dimensions. It was 7 feet through 10 feet from the stump, and 5 feet through 50 feet from the stump. 22 logs were taken from the tree, the average length of which were 12 feet. 14 feet of the tree were spoiled in falling. The extreme length of the tree from the stump to the top twigs was 300 feet. Greenfield Gazette, quote, "In 1995 Robert Leverett and Wublosen measured the Boogaman pine, a white pine in Great Smoky Mountains National Park, at a height of 207 feet in 1995 using ground-based cross-triangulation methods. This the highest accurate measurement obtained for any tree in the eastern United States within modern times. The top of the tree was lost in Hurricane Opal in 1995 and it currently stands at just under 190 feet in height. It is possible that some white pines in the past reached heights of well over 200 feet given the much larger area of primary forest prior to the timber boom in the 1800s. However, based on what grows today, it is highly unlikely they ever reached the heights in some of these historical accounts. These reported heights are likely just a mixture of personal and commercial bravado by the lumbermen of the time. Approximate tree heights. Of the various methods of approximating tree heights, the best options are requiring only a minimal amount of equipment are the stick method and the tape and clinometer method. To get accurate measurements with either method, care must be taken. First, try to view the tree from several different angles to see where the actual top of the tree is located. Use that point for the measurements. This will eliminate the greatest potential for error. Stick method. The stick method requires a measuring tape and a stick ruler and uses the principle of similar triangles to estimate tree heights. There are three primary variations of the stick method. A. Stick rotation method, a pencil method for trees on level ground and with top vertically over the base. 1. Grasp the end of a stick and hold it at arm's length with the free end pointed straight up. 2. Move back and forth toward or away from the tree, to be measured until the base of the tree aligns visually with the top of the hand at the base of the stick and the top of the tree is aligned with the top of the stick. 3. Without moving the arm up or down, rotate the stick until it is parallel to the ground. The base of the stick should still be aligned with the base of the tree. 4. If you have an assistant, have them walk away from the base of the tree at a right angle to your position until they reach the spot on the ground that aligns with the top of the stick. If alone, pick a distinctive point on the ground to mark this point. The distance from the base of the tree to this point is equal to the height of the tree. Again, this method assumes that the top of the tree is vertically over the base. B. Standard stick method. 1. Find a straight stick ruler. 2. Hold the stick vertically at arm's length, making sure that the length of the stick above your hand equals the distance from your hand to your eye. 3. Walk backward away from the tree. Stop when the stick above your hand exactly masks the tree. 4. Measure the straight line distance from your eye to the base of the tree. Record that measurement as the tree's height to the closest foot. As with A, if the top is not vertically over the base, this method will generate an error. C. Advanced stick method uses the same procedure outlined above with the addition of a few measurements and some basic multiplication. This method does not require that the length of the measuring stick be the same as the distance from your bottom hand to your eye, so it can be used in more varied settings to get a height measurement. 1. Holding the stick as outlined above. Align both the base of the tree with the top of your hand, holding the stick, and the top of the tree with the top of the stick. You can do this by moving toward or away from the tree, adjusting the stick length, and by moving your arm up and down. 2. Once aligned, measure the distance from the top of your hand grasping the base of the stick to your arm. 3. Measure the distance from the top of your hand to the top of the stick. 4. Measure the distance from your eye to the base of the tree, so long as the yardstick is held straight up and down and the top of the tree is vertically over the base. The various measurements are still proportional, and then you can calculate the height of the tree using a simple formula equals tree height. Using this formula, the height of the tree can be calculated no matter what angle you are holding your arm, and no matter what the length of the yardstick that extends above your hand. This has a big advantage if you are measuring a tree on uneven ground or if you can only measure the tree from a single angle. One problem that also often occurs is in order to see the top of the tree, the surveyor must be farther away from the tree than possible using a yardstick length of 23 to 25 inches. Using the simple formula above, a smaller length of stick can be used, allowing the surveyor to actually see the top of the tree. as with A and B above. This method assumes that the top of the tree is vertically over the base. If this assumption is violated, the triangles will not be similar and the ratio and proportion relationship of the sides of similar triangles will not apply. Clinometer and tape method. The clinometer and tape method of the tangent method is commonly used in the forestry industry to measure a log length. Some clinometers are handheld devices used to measure angles of slopes. The user can sight to the top of a tree using such a clinometer and read the angle to the top using a scale in the instrument. Topographic abney levels are calibrated so when read at a distance of 66 feet from the tree, the height to the tree above eye level can be directly read on the scale. Many clinometers and abney levels have a percent grade scale that gives 100 times the tangent of the angle. This scale gives the tree height in feet directly when measured at a distance of 100 feet from the tree. In general, the clinometer is used to measure the angle theta from the eye to the top of the tree, and then the horizontal distance to the tree at eye level is measured using a tape. The height above eye level is then calculated by using the tangent function. Horizontal distance at eye level to the tree x tangent theta equals height above eye level. The same process is used to measure the height of the base of the tree above or below eye level. If the base of the tree is below eye level, then the height of the tree below eye level is added to the height above eye level. If the base of the tree is above eye level, then the height of the base of the tree above eye level is subtracted from the height of the tree top above eye level. It may be difficult to directly measure the horizontal distance at eye level if that distance is high off the ground or if the base of the tree is above eye level. In these cases, the distance to the base of the tree can be measured using the tape along the slope from eye level to the base of the tree and noting the slope angle theta. In this case, the height of the base of the tree above or below eye level is equal to the horizontal distance to the tree is. Errors associated with the stick method and the clinometer and tape method. Aside from the obvious errors associated with bad measurements of distances or misreading the angles with the clinometer, there are several less apparent sources of error that can compromise the accuracy of the tree height calculations. With the stick method, if the stick is not held vertically, the similar triangle will be malformed. This potential error can be offset by fastening a string with a small, suspended weight to the top of the stick so that the stick can be aligned with the weighted string to assure it is being held vertically. A more pernicious error occurs in both methods where 1. The tree top is offset from the base of the tree, or 2. Where the top of the tree has been misidentified. Except for young, plantation-grown conifers, the top of the tree is rarely directly over the base. Therefore, a right triangle used as the basis for the height calculation isn't truly being formed. An analysis of data collected by the Native Tree Society of over 1,800 mature trees found, on average, the top of the tree was offset from the perspective of the surveyor by a distance of 8.3 feet, and therefore was offset from the base of the tree by around 13 feet. Conifers tended to have offsets less than that average, and large broad-canopied hardwoods tended to have higher offsets. The top of the tree therefore has a different baseline length than the bottom of the tree, resulting in height errors equals height error. The error almost always incorrectly adds to the height of the tree. For example, if measuring a tree at an angle of 64 degrees, given an average offset of 8.3 feet in the direction of the measurer, the height of the tree would be overestimated by 17 feet. This type of error will be present in all of the readings using the tangent method, except in the cases where the highest point of the tree actually is located directly above the base of the tree, and except in this unusual case, the result is not repeatable, as a different height reading would be obtained depending on the direction and position from which the measurement was taken. When the top of the tree is misidentified and a forward-leaning branch is mistaken for the tree top, the The height measurement errors are even larger because of the bigger error in the measurement baseline. It is extremely difficult to identify the actual top branch from the ground. Even experienced people will often choose the wrong sprig among the several that might be the actual tree top. Walking around the tree and viewing it from different angles will often help the observer to distinguish the actual top from other branches. But this is not always practical or possible to do. Major height errors have made it onto big tree lists even after some degree of vetting, and are often wrongly repeated as valid heights for many tree species. A listing compiled by the NTS shows the magnitude of some of these errors. Water hickory listed as 148 feet, actually 128 feet. Pignut hickory listed at 190 feet, actually 123 feet. Red oak listed as 175 feet, actually 136 feet. Red maple listed at 179 feet, actually 119 feet, and these are only a few of the examples listed. These errors are not amenable to correction through statistical analysis as they are unidirectional and random in magnitude. A review of historical accounts of large trees and comparisons with measurements of examples still living found many additional examples of large tree height errors in published accounts. Sign height or ends method. Many of the limitations and errors associated with the stick method and the tangent method can be overcome by using a laser rangefinder in conjunction with a clinometer, or a hypsometer, which incorporates both devices into a single unit. A laser rangefinder is a device which uses a laser beam to determine the distance to an object. The laser rangefinder sends a laser pulse in a narrow beam toward the object and measures the time taken by the pulse to be reflected off the target and returned to the sender. Different instruments have different degrees of accuracy and precision. The development of laser rangefinders was a significant breakthrough in a person's ability to quickly and accurately measure tree heights. Soon after the introduction of laser rangefinders, the utility in measuring trees and use of the sign-based height calculations was recognized and adopted independently by a number of big tree hunters. Robert Van Pelt began using a criterion 400 laser circa 1994 in the Pacific Northwest of North America. The instrument had a pre-programmed tree height routine based upon the tangent method, but he used the alternate vertical distance mode, essentially the sign method with no frills to measure tree heights. Began using an optical rangefinder and Suunto clinometer circa 1993-94 using the sign method. About a year later he purchased a Bushnell lighter speed 400 laser rangefinder and began using it in tree measurements. Robert T. Leverett began using laser rangefinders in the eastern United States in 1996. He and Woblosen had previously been using cross-triangulation methods to measure tree heights prior to adopting the laser rangefinder techniques. The first publication describing the process was in the book Stalking the Forest Monarchs, A Guide to Measuring Champion Trees, published by Woblosen, Jack Sobin, and Robert Leverett in early 1997. The technique was soon adopted by other big tree surveyors in other areas of the world. Brett Mifsud writes, new techniques for measuring tall trees were used in this study. Initially, a Bushnell 500 yardage Pro laser rangefinder was used in conjunction with a Suunto clinometer to estimate tree heights in all regions. The previously used simple tan method of measuring tall trees was discarded in favor of the sign method. Currently, this method is being used by tree researchers measures and surveys in Asia, Africa, Europe, and South America. Using the rangefinder and clinometer, only 4 numbers are needed to complete the tree height calculation, and no tape is necessary, nor is direct contact with the tree. The readings are 1. The distance to the top of the tree measured using the laser rangefinder. 2. The angle to the top of the tree measured with the clinometer. 3. The distance to the base of the tree measured with the laser rangefinder. And 4. The angle to the base of the tree measured with the clinometer. The calculations involve some basic trigonometry, but these calculations can easily be done on any inexpensive scientific calculator. Situations where the top of the tree being measured is above eye level and the base of the tree being measured is below eye level is the most common situation encountered in the field. The other 2 cases are those where both the top of the tree and the base of the tree are above eye level, and where both the top of the tree and base of the tree are located below eye level. In the first situation, if D1 is the distance to the top of the tree as measured with a laser rangefinder, and is the angle to the top of the tree measured with the clinometer, then this forms the hypotenuse of a right triangle with the base of the triangle at eye level. The height of the tree above eye level is. The same process is used to measure the height or extension of the base of the tree above or below eye level, where D1 is the distance to the base of the tree and is the angle to the base of the tree. Therefore, the vertical distance to the base of the tree above or below eye level is. Common sense should prevail when adding H1 and H2. If the base of the tree is below eye level, the distance it extends below eye level is added to the height of the tree above eye level to calculate the total height of the tree. If the base of the tree is above level, then this height is subtracted from the height to the top of the tree. Mathematically, since the sign of a negative angle is negative, we always get the following formula: height equals sin x, sin x. There are some errors associated with the sine top, sine bottom method. First, the resolution of the laser rangefinder may range from an inch or less to half a yard or more, dependent on the model being used. By checking the characteristics of the laser through a calibration procedure and taking measurements at only the click-over points where the numbers change from one value to the next highest, much greater precision can be obtained from the instrument. A handheld clinometer can only be read to an accuracy of about 1/4 of a degree, leading to another source of error. However, by taking multiple shots to the top from different positions and by shooting at the click-over points, accurate heights can be obtained from the ground to within less than a foot of the tree's actual height. In addition, multiple measurements allow erroneous values where the clinometer was misread to be identified and eliminated from the measurement set. Problems may also occur where the base of the tree is obscured by brush. In these situations, a combination of the tangent method and sine methods may be used. If the base of the tree is not far below eye level, the horizontal distance to the tree trunk can be measured with the laser rangefinder, and the angle to the base measured with the clinometer. The vertical offset from the base of the tree to horizontal can be determined using the tangent method for the lower triangle, where, in these cases where the tree is fairly vertical and the vertical distance from the base of the tree to eye level is small, any errors from using the tangent method for the base are minimal. There are considerable advantages to using this method over the basic clinometer and tape tangent method. Using this methodology, it no longer matters if the top of the tree is offset from the base of the tree, eliminating one major source of error present in the tangent method. A second benefit of the laser rangefinder technology is that the laser can be used to scan the upper portions of the tree to find find which top is actually the true top of the tree. As a general rule, if there are several readings from different tops of the tree at a near the same inclination, the one that is the farthest in distance represents the tallest top of the group. This ability to scan for the highest point helps eliminate the second major source of error caused by misidentifying a forward-leaning branch at the wrong top. Additionally, aside from gross errors resulting from misreading the instrument, the results will not overstate the height of the tree. The height can still be undermeasured if the true top of the tree is not correctly identified. The sign top, sign bottom method allows the height of trees to be measured that are entirely above or below the eye level of the surveyor as well as on level ground. A tree can also be measured in segments where the top and bottom of the tree are not both visible from a single location. A single height measurement takes only a matter of a few minutes using separate laser rangefinder and clinometer, or less when using instruments with a built-in electronic clinometer. The measurements made using these techniques, through averaging multiple shots, are typically within a foot or less of climber-deployed tape measurements. Some laser hypsometers have a built-in height measurement function. Before using this function, the user should read the instructions on how it works. In some implementations, it calculates tree heights using the flawed tangent method, while in others it allows you to use the better sign top, sign bottom method. The sign top, sign bottom method may be called the vertical distance function or a two-point method. For example, the Nikon Forestry 550 implements the sign top, sign bottom method only, while the success of the Forestry Pro has both a two-point measurement and a three-point measurement function. The three-point measurement function uses the tangent method, while the two-point method uses the sign top, sign bottom method. The top and bottom triangles are automatically measured using the two-point function and added together, giving an accurate height measurement. A more detailed discussion of the laser rangefinder clinometer sign method can be found in Blazon and Franken in discussions on the Native Tree Society website and BBS. Reviews of the sign method have been published by U.S. forest researcher Dr. Don Bragg. He writes, when heights were measured properly and under favorable circumstances, the results obtained by the tangent and sign methods differed only by about 2%. Under more challenging conditions, however, errors ranged from 8 to 42%. These examples also highlight a number of distinct advantages of using the sign method, especially when exact tree height is required. And under typical circumstances, the sign method is the most reliable means currently available to determine standing tree height, largely because it is relatively insensitive to some of the underlying assumptions of the tangent method. Unfortunately, only recently has technology permitted the use of the sign method, whereas the tangent method has been ingrained into procedures and instrumentation for many decades.